presentation, which is an honor to me. And in this talking, I will present the work Indirect test, tensile test, and size effect of concrete. But mainly, I will focus on the Brazilian test and some results of the research, which is still under development in collaboration with Professor Jaime Planas and the student Camilo Ramos. The outline during my presentation will be the following. First, I will start with an introduction and presenting the main aspects of the Brazilian test. Then I will move to the size effect and new materials. And then I will present the numerical study, which is still under development, for the extension of the size effect curves of concrete. I will present the results and finally the conclusions. So let's start with the introduction. Let me start commenting that direct tensile tests are apparently the most straightforward way to determine the tensile strength of concrete. In those, a tensile strength stress is applied, and the traction separation law of the material is obtained without the need of performing an inverse analysis. However, failure out of the plane can occur, as Professor Planas already explained in his presentation, with the subsequent loss of symmetry leading to eccentricities at the fracture process zone, which was reported in the 90s by Hordick and Nogabay. It implies that a bidimensional analysis might not be completely accurate. For this reason, indirect tests are commonly used because they solve those problems. An indirect tensile state is produced, and they are much easier to be performed. However, they are not perfect, of course, and interpretation of the results may be difficult. And not always the tensile strength can be determined from the maximum load of the test. Now, let me present the Brazilian test, which is an indirect test, also known as diagonal compression test. In this case, a compression load is applied through two bands. I don't know if you can see those, the mouse moving through the screen. And then the specimen is supposed to split into halves. And this test is an adequate solution to determine the tensile strength of quasi-brittle materials. As demonstrated by Rocco and collaborators in the 90s, the ultimate load occurs for a load very close to the initiation of cracking. But it happens only if some conditions are followed. First, the loading rate has to be limited to this range, 500 to 1000 kilopascals per minute, and it was obtained according to the results of some experiments. As we can see in this figure, the tensile strength inferred from the experiment approaches the actual value obtained in a stable test, just below this load speed. The second condition is that the bearing strips have to be narrow and limited to the 4 to 8% of the specimen size, which was obtained again from experimental results. Let me show here only the results for cylindrical specimens, although the research of Rocco includes also results for cubic specimens. And we see that for different configurations of the test with different widths of the bearing band B, the tensile strength inferred from the test is much higher than the true tensile strength as the bearing band width increases, and this is the reason to limit the width of this band. We can observe as well that there is a marked size effect if we see the curves. The difference between the tensile from the splitting test, the tensile strength from the splitting test and the true tensile strength increases as the ratio DL1, which I will define later and was already defined by Professor Planas. When this ratio decreases, the difference of the tensile strength increases. It implies shorter specimens or less fragile. So now let's move to the next point, size effect and new materials, because the previous results I commented were obtained for ordinary concrete. But however, in the last decades, there has been a great improvement of concrete mixtures, and emergence of new materials has shown that research about the fracture behavior is necessary. In particular, a recent study in collaboration with the Spanish Association of Railway Sleeper Element Manufacturers manifested the need of extension of the size effect curves in the case of the Brazilian test. In that work, a particular implementation of the method proposed by Planas Guinea analysis, which will be presented in the next slide, was proposed to determine the breathness of the mixtures in the factories. The results obtained show that the parameters of some mixtures are out of the ranges considered, and the precision of the method, the experimental method, has to be determined. So this is the reason of the current research, which I will present later, consisting in an extension of the size effect curves of the Brazilian test, but in this presentation I will focus only on the results of cylindrical specimens. So let me show you the background of this work, which motivated the current research. And let's start with a very short review of the methods proposed by Planas Guinea analysts in 2002, which consists in a method of indirect test for obtaining a stress crack opening curve of concrete. This method is published indeed in the final report of Relent Technical Committee 187 SOC, and already in the proposal submitted to the ASI Committee 446, which is still under revision. This method relies on the cohesive crack model, which has been extensively explained during the previous presentations of this symposium, especially by Professor Planas, but I will just mention that according to this model, when a crack appears as at the most unfavorable section, this crack transmits stresses across its faces, following a softening curve in which the stress is depending on the crack opening. So in the method by Planas Guinea analysis, two types of indirect tests are proposed. First, Brazilian test, as those in this image, and three-point bending test. From the Brazilian test, the tensile strength is obtained. It is supposedly sufficiently close to the true tensile strength of the material if the recommendations by Rocco, which I already mentioned, are followed. And then from the three-point bending test, together with the result of the Brazilian test, an inverse analysis is performed, and we obtained the main fracture parameters of concrete, and in particular the parameters to define a bilinear approximation of the softening curve, as that is sketched in that figure. So to continue with the background, this method was applied in a study carried out in collaboration with the Spanish Association of Railway Sleeper Element Manufacturers, with results published just 2 years ago. And in that work, the objective was to determine the fracture parameters of pre-stressed railway sleeper elements in the factories. So a particular implementation of the test proposed by Planas were adopted here in this work just by using the factory facilities. It has some limitations because we don't have all the instruments normally available in a research laboratory. In particular, the specimen geometry was modified for three-point bending test. Prisms were used as those of the Spanish factories, and for the Brazilian test, cubes instead of cylinders, just because they are specimens normally used in the control test of the factories. And the tests were run only up to maximum load. It implies that we obtain only information about the first branch of the bilinear curve, the curve in red here, but this is adequate to describe the behavior of thin cracks, those with width smaller than this parameter W1, the intersection with the abscissas axis. And moreover, from this type of experiment, we can compute the breathless length, which is one of the main fracture parameters of concrete, and is calculated according to this formula. And you can see that the parameters in the calculation are this crack opening, characteristic crack opening, and the tensile strength. So we see that this is an inverse measurement of the breathlessness of a mixture, as the slope is sharper, more brittle, and it implies a smaller breathless length. This method was verified by performing a round-robin test in collaboration with 11 participants, and 156 specimens were tested. The results were satisfactory just about the feasibility and reliability of the method, and moreover, it provided the opportunity of verifying the experimental method of indirect test proposed by Planas et al. But however, one of the conditions of the method was not verified for some mixtures. The condition, which is here, of a limit of the ratio of the size specimen versus the breathless length for the Brazilian test. It implies that there is a high error in the estimation of the tensile strength, which cannot be neglected. If we see now here the size effect curves proposed by Rocco et al., those were obtained from computations, and here we have the two graphics for cylindric and for cubic specimens. The same effect that, as I commented before, occurs for the cubes. There is the error increases as the bandwidth increases and as the ratio DL1 decreases. And in particular, for the experimental values recorded in this work, we are here. For this ratio, it was obtained, and then this condition was not verified. So what can we do in this occasion? Well, to control the error of the test, one possibility is to increase the size of the specimen, but this was not a practical solution because we want to use the factory facilities and to keep the specimen size. So another possibility is using these curves to correct the obtained value for the tensile strength through an iterative method. So we did that, and the final ratio with the improved values of L1 and FT was 0.33, which unfortunately is out of the range of applicability of these iterative methods, because Rocco only included ratios up to 0.4 because they were the normal values for the concrete mixtures of the night available in the 90s. So here comes the need of extension of the size effect curves. So now I will present very briefly the numerical study that is under development currently. I will start